Okay, everybody, here's lesson 2 on circles, inscribed angles, and stuff that happens with tangents. You'll probably hear me say this a lot, but this is the first lesson of many that seem like people have a hard time just seeing the things. Like, yeah, I don't know what my best advice is on this stuff, but it just seems like these things get kind of invisible. Then when I hand back quizzes and tests, people are like, oh my gosh, why didn't I see that? And it happens every year in this unit, and I'll just kind of warn you about that right away. Anyway, the first one is, I think one of the coolest rules we have about circles is the thing about inscribed angle. So an inscribed angle, gosh, it's cool how I can rotate this. Inscribed angle is an angle where the vertex is on the circle itself, which is what makes it an inscribed angle. We talked about central angles before, where the angle is at the center of the circle, but this is not that. This is inscribed angle. Well, the inscribed angle, and here's the theorem about it. Can I get this to straighten out? The theorem about the inscribed angle is that the measure of this angle is exactly half of this arc out here. And remember that arc, they don't say this here, but I think it would be kind of nice if they did. The arc gets its measure from the angle that does happen at the center. So if we could draw a central, that's not really very straight. If we could draw a central angle, that angle is kind of like, if this is x, this is going to be 2x. Yeah, so that's what that looks like. Yeah, and I can also show you this in Sketchpad. I can't do it on this iPad really quickly, but I could do it on... Why can't I turn this? Everything is just a little bit, sideways here. All right. Anyway, that's the cool theorem about that. It's kind of surprising. Again, it's one of those things people just don't see in pictures sometimes. It's like, how did I miss that? Okay, so we'll do that a lot, and lots of practice about that. So if that's going to be half the arc, if two angles intercept the same arc, both of these are going to be equal because they are both half of whatever this is. So if that's 2x degrees, that's going to be x degrees, and that's going to be x degrees. Yeah, yeah, and it doesn't matter where we put this vertex. If that angle, and I draw them, I like to draw them longer, just because, it's easier to see the whole angle like that. All these angles are exactly the same, because they all are intercepting. It's like the angle that's in its, or the arc that's in its mouth. They're all exactly the same, so those have to be the same size angle. And it's kind of a surprising fact, actually. Again, when I show you on Sketchpad, I think you're gonna be amazed that that's actually true. Okay, and if it happens to intercept an arc that's exactly a semicircle, that's 180 degrees, and so just by applying the same rule, we know that that has to be 90. Well, that happens in a very kind of special case, and it happens enough that we make a rule about it. It happens whenever this is a diameter. If that's a diameter, then you know this to be a right triangle. So no matter what kind of triangle I want to inscribe in a semicircle, it's always going to be a right triangle. Okay. All right. Are we not sideways anymore? That's good. Quadrilateral, inscribed in a circle, then its opposite angles are supplementary. Okay, so this angle and that angle have to make 180. That's not a really good zero. That makes, those two make 180 together, and these two make 180 together. So the angles that are opposite each other in the inscribed quadrilateral. I am going to prove this in class. It's kind of an easy proof to show, but that's something I can do on video. Or sorry, not on video. I can do that. Whoa. Let's do this. Just remind myself that we will do the proof in class. Maybe I'll ask you to start by thinking about that. All right, let's do some of these actual calculation-y stuff. Okay, so if this is 20, this is an inscribed angle. It's inscribed in the circle, and if we apply that rule we were just learning about, this is 40 degrees. This angle is inscribed in a circle, and it's sort of got this 110 in its mouth. So this thing has to be 55. What were we supposed to find here? ABC. Oh, ABC, I don't know yet. ABC is this whole thing. Well, that's got this arc in its mouth. And now I know what this whole thing is. It's 150 altogether. So, whoops. So measure of angle ABC is 75 because it's half of this. Isn't that fun? But I think maybe what part of the problem is about these kind of pictures is that the answer that you seek, the key in the picture that you're looking for is completely on the other side of the circle. Like this 110 This 110 goes completely with this 55, and they are on opposite sides of the picture. And people get fixated, I think, in one corner of the picture, and they're kind of looking for one thing, and they just don't see it because it's way on the other side, and it kind of catches them off guard. I think that might be part of the problem. All right, find x, y, and z. Here we go. I just automatically start filling stuff in when I see it. So this is a 51. That means we have 102 degrees out here. This thing is 27, which means this arc is, what is that, 54? I think it's 54. We have a diameter here. That's helpful. Diameter means we have 180 in places, so that's 78. And this is the rest of a circle over here. Makes 6. I can't do math in my head. 126. Okay. What am I supposed to find? X, Y, and Z. Oh, if this is 54, this is 27. I could have known that without knowing the 54. Notice how the angles at F and H both intercept that same arc, so I didn't really even need to know the 54 to know they were equal. Y is half of the 78. See how that's already kind of across the circle right there. And Z is half of the 126. Now, I could have gotten that 39 from knowing this is a right angle. That's fine. Z is half of... I could get Z in a triangle with 180. That also works still. Anyway, half of 126 is 63. Sorry, this is so small. Okay, I should save some for us to do together in class. I don't want to have all the fun. Yeah, so let's do that. Let's save some of these for in class. Oh, you know what? I do want to do 4. 4 has got a feature in it that always gets people. They don't really have. Okay, that rule about the inscribed angles. Okay, so this we said already is half of this. That's also true if it's actually right on a tangent. So if I drew a tangent line here and a angle right there, this angle is half of this arc. It's kind of the special case limit at infinity kind of version of this rule, but you have to realize it's still the same thing. And when I show you on Sketchpad, I can show you how that works. So this x right here, that's right here on a tangent, that I know is exactly half of this, and this y right here tells me that this is also 2y. All right, so if 2x is across from this 60, that tells me that 2x is 120 from the 60. 140 here points at this angle, so this is 70. Oh, x is half of 120, so that's got to be 60. Now I have 180 on this line, making this thing 50. Yeah. Again, the hardest thing to see there, I think, is this tangent rule thing. I think we're done with that, right? Okay. Yeah, I don't want to do, again, I don't want to have all the fun today. I think, why am I drawing? I don't want to draw. This is the opposite angles in the quadrilateral. Maybe we'll do one of those. I'm going to keep 6. I'll keep 6 for in class, but we can do 5 right now. So 68 and y, those are supposed to make 180, so this has to be 112. Also, x and that one over there, the angle at C, have to make 180. But I don't know much about those yet. I do know that 94 here would be, if I were to draw this angle right here, one way to do this, I know this has to be 40, half of that, 45, 47, right there. The 112 is down there. Doesn't really help me. What else can I do here? Okay, that's 94, 47, talking to myself. Another way I could do this is look at this 68. 68 is half of this arc. So if that whole thing, if that arc is 68, sorry, this angle is 68, this whole arc over here is 136. Gosh, math is hard today. So this is supposed to be 90. That kind of helps. Oh yeah, I didn't need to do this. I didn't need to do this across the quadrilateral thing, because now I know, different color, the arc from D to E, I can figure that out. That is now 184. And this arc, or sorry, this angle here at C would then have to be half of that, which is 92. And then opposite angles here in the quadrilateral, that makes this 88. That was kind of fun. Yep, I probably could have done it by chopping this thing into two triangles with the segment from C to F, but I didn't have to. Okay, next section in the geometry book today is about tangents. Tangent is a special line, and we kind of already talked about it with the intercepted arc or intercepted angle rule. Tangent is a special line that goes right along a circle and hits it in exactly 1 point. You probably heard of those before. Anyway, the theorem here is that, yeah, that's going to be perpendicular to a radius at that point. Not perpendicular to everything at that point. It's just perpendicular to a radius, which is kind of helpful to know. Hey, here's another example of that rule we just learned. Realize that this would be 180. Here's another kind of example how that's half of the intercepted arc. Yeah, you could apply that theorem and kind of say that's why it's 90. And the other thing about tangents is that if you have a point outside the circle and you draw the tangent to the two places that could possibly be tangent to the circle from the same point B, those things have to be equal. That's not really that hard to prove. Imagine drawing a radius there and a radius there. These have to be 90. And we could draw this in here. We have a nice little kite going on. Of course, I'm trying to prove that this is congruent to this. But I could, without knowing that, I could get that pretty quickly by knowing that I have congruent triangles here and here by, what would that be, HL? Yeah, HL would give me congruent triangles there, and then CPCTC gives me AB congruent to CB. All right, last page. Yeah, this is kind of a, whoops, yeah, this is kind of a, what am I trying to say, typical kind of picture. You're going to see this a lot. And realize with the thing we just learned, that segment has to be congruent to that segment, this little segment has to be congruent to this little segment, etc. So, yeah, those are fun. Those are going to come up a lot. I got my my page is just a little bit turned again. It's okay. Segment OT is tangent. Now they have to like centers of the circle. They have to tell you if it's tangent. You can't just assume that it's tangent, or if it looks tangent, you can't really be sure. There's some fun problems where they look really tangent on coordinates, but you can prove whether or not they actually are. All right, so OR is 6, OT is 10. We're supposed to find RT. Well, I know this is a right triangle because it's tangent, and I also know that, well, I guess that's all I need to know, right? I was going to say, well, we also know this is 6. That actually isn't very helpful right now. I'm supposed to find RT, so I just have to do Pythagorean theorem. Whatever that is. That's the square root of 136, whatever that is. My square root symbol doesn't look that great. We will do this one in class. Same trick, I'm sure. And this looks like a fun one to do in class, too. I don't want to have all the fun. Okay, I will see you soon.